All right, welcome back, everybody. Today, this section, we're going to talk about Green's theorem, which is kind of like another fundamental theorem. Okay, it relates a line integral to an area integral. And it's stated as follows. Let C be a positively oriented, that means counterclockwise, piecewise smooth, okay, that means basically differentiable, okay, simple closed curve, that just means like a loop. Doesn't have to be a circle or an ellipse, but just something that has the same endpoint. Something that starts where it finishes. Okay? In the plane. And let D be the region bounded by C. Okay? If P of xy and Q of xy have continuous partial derivatives, on any region bounded by, on any region containing D, then, okay, now we're going to get to the statement. The integral, and we're going to write it with a circle to mean it's basically a loop integral, that's what they're called, of P dx plus Q dy equals the integral over the area of partial P with respect to y, x, I always screw this up, partial Q with respect to x, minus partial P with respect to y dA. And that's the area integral. Okay, so let's do this. Usually the proof we use a square. So we're going to do a proof over a square. Okay, so let's start. I'm going to draw a little picture. Okay, so let's say we have a square here. So let's say that's 1, 1. This is 1, 0. This is 0, 1. I know it's a bad square. Okay, positively oriented means it's going to go this way. Okay, positively oriented, like that's a counterclockwise movement. Okay, one way to think about it is you think about the inside of your curve being to your left if you're moving positively. Okay, so I like to think of our curve here. Our curve is actually moving in 5 different ways. So I'm sorry, 4 different ways. Okay, gamma 1 you can think of it as that's t0, where t goes from 0 to 1. Gamma 2, that's actually going to be 1 comma t, where again t goes from 0 to 1. So I want you to think about what's going on here. From here to here, if you're going to move from here to here, you're moving along this curve, and your x is just going to be t, and your y is not moving at all, so that's why y is 0. I mean, it's not just not moving, but it's on y equals 0. Here, your y goes from 0 to 1, so that's why y is t, but your x is not moving, it's just stuck at 1. So gamma 3, well here, y is 1, and x is coming back in the other direction. So I'm going to write this as x is 1 minus t, y is 1, and t still goes from 0 to 1. And then gamma 4, well, along gamma 4, x is 0, y is 1 minus t, t goes from 0 to 1. Okay? So we've just parameterized each piece of this separately. Okay? Now, our integral. Let me make this a little bigger. Our integral over c. I'm writing it again with the circle for the fact that it's like a loop integral. It's an integral over a curve that will start at the same place it ends. Okay. Oops. Of p dx plus q dy is equal to. Now, this is going to be the integral over gamma 1. So the integral over gamma 1, so that's this integral. Well, dx is just dt, and dy is 0. So what am I going to have? P of t comma 0 dt from 0 to 1 plus, now from here, gamma 2. The gamma 2 integral is going to be from 0 to 1, and there dx is 0. So it's going to be q of 1 comma t dt. Write this. This is our gamma 1 integral. This is our gamma 2 integral. We're going to have a gamma 3 integral. From here to here. So that's going to be dx is going to be negative dt because it moves that way, or because of the minus. Okay, so you're going to have p of 1 minus t, 1, and then with negative dt. Okay, remember y along this curve is 1. Okay, now this piece is going to be plus the integral from 0 to 1, q of 0, 1 minus t dt. Okay, so let me just write this. This was our gamma 3. This was our gamma 4. Okay. Next. So what we're going to do, we're going to put common pieces together. So we're going to put this together with this together with this. Okay, so we're going to get the integral from 0 to 1 of p of t0, oh, not the dt yet, because we're going to put that together with something. Now, we're putting that together with this, so we're going to write minus, because of this minus, p of 1 minus t, 1 dt. So far, okay? All right, plus let's put the q terms together. The integral from 0 to 1 of q of 1t dt. Ooh, I made a mistake on gamma 4. That should have been a negative dt. I'm sure that you were all noticing that while you were watching the video. And the reason was, of course, because here dy would have been negative dt. So that saves us, otherwise it wouldn't have worked. This needs to be minus q of 0, 1 minus t dt. Okay, so far so good? All right, that's what I like to say. Okay, so next, what we're going to do, just give me just a second. Okay, now we're going to do a substitution here. It's a little bit weird. Let's just make sure we know what's going on. Here, this substitution, let me just write it out. Am I going to have space? Yeah, let me write it out. So let me write it out up here. So let's do negative integral from 0 to 1 p of 1 minus t dt. So if we do a substitution here of u equals 1 minus t, watch what happens. This is going to be the integral. Now, these limits are actually going to change, aren't they? Let's keep the negative sign from in front before. I need to move things around a little bit. Okay. Our original negative sign. Now, when t is 0, u is 1. And when t is 1, u is 0. So it's going to be from 1 to 0. We have p of u. Now, I'm not changing this one. I'm just changing the integral here. The reason is because that should have been a 1. Right? Over here it was a 1. So, p of u, 1. And now, du is negative dt. So we'll have du and then positive. Okay, but now look, doesn't that equal from 0 to 1 p of u1 du? Oop. Okay, and now that just means this integral, I can just change it. I can just change this u back to t. So I'm going to get the integral from 0 to 1 p of t0 minus p of t1 dt plus the integral from 0, 1. I can do the same game over here. Okay, doing the same game over there. Now, here's a nice little thing though. Notice something. These are the same in the x, but in the y's they're different, right? Here they're the same in the y, but in the x they're different. This is the same as writing from 0 to 1, then from 0 to 1. Which derivative? This is the negative of the derivative of p with respect to y. Here, from 0 to 1, 0 to 1, this one, this is the integral of the derivative of q with respect to x. Okay, and now let's take a look. Let me rewrite that. Well, first, dt, I can replace that by dx because that's in the first coordinate here. Here, dt, I can replace that by dy. So we get, running out of space, but that's okay because we're almost done. The integral from 0 to 1, 0 to 1, partial q with respect to x minus partial p with respect to y. And then I'm not worrying about the order anymore. And that was our original statement. So that's Green's theorem. Okay. All right. Good to go.